Hello folks, thank you for tuning in, or I suppose it's not really tuning in, is it? But thanks for watching. Sorry that I'm ever so slightly delayed on this. Unfortunately, I did have one or two last minute hitches, but everything seems to be working now, so hopefully I'm ready to get started. I see that there's quite a few people who are already watching. That's excellent to see everyone. And so I'm just going to get straight into it. Remember, this is the AQA 2016 June P2 higher question paper, which I'll be doing. If you check in the previous video, there are the links to be able to get that paper and the mark scheme if you're wanting to follow through at home. One other thing which... Excellent, I've dropped my pen lids. One other thing which I want to mention before I get started, and that is, I did say that I was going to let people choose what they wanted to see in the next video, which paper that they wanted me to do. If you go to strawpoll.me/Mr. Thornton UK, there are a series of questions on there to let you choose whether you want me to do higher or foundation, which exam board you'd like me to do, and so on. I'm going to keep that link open until 6 PM UK time tonight, so you've got plenty of time to go and view and then make your vote after this video's done. And then at 6 PM I'm going to announce it. I'm going to be announcing it on Twitter, which you should be able to see. Let me just check on my screen. Just here, you can see my Twitter account ID. If you go on there, after 6 PM, I'll have announced which one of the options won and which paper I'll be doing in the next live stream. Whew, bit nervous doing this, as you might be able to tell. What was the other thing I was going to say? Oh yes, I'm not sure exactly yet when the next live stream is going to be. I haven't decided yet. I need to look at my timetable and what meetings I've got over the course of the next week. But I'll post a tweet and I'll post a video to let you know when it's going to be a little bit later on this week. Okay, so let's get started. So the first question on this paper, a student investigated how the speed of a ball bearing changes as the ball bearing falls through a tube of oil. And we've got a picture of the ball bearing falling through this. Oh, and I should mention as well, I haven't actually looked at this question paper yet, and I've been teaching the Edexcel's specification for the past year, so I'm a little bit out of the loop with AQA, not that much. I have taught it quite a lot in the previous years that I've been teaching. So this is genuinely a paper which I'm not sure whether I know all the answers to or not. I've not looked at it before. I do know that I need to get 46 out of 60 to get an A star. I'm hopeful that I'll be able to get that. I'm not certain that I'll get 100%, but I'll try. I'm going to go through each question and then I'm going to have a look at the mark scheme and let you know whether or not I would have got the marks there. And I'm going to try to be as unbiased as possible. Okay, so we've got the ball bearing falling through the tube of oil. The student measured the time taken for the ball bearing to fall different distances. Each distance was measured from the top of the oil. So this is going to be a question all about experimental technique and possible sources of error. And you can see that the first question there is actually talking about what's the main source of error in this investigation. If you see something where they're describing an experiment which you haven't necessarily done, I mean, some of you may have done this, but not everyone will have done, then assume that they're going to be asking you about experimental technique rather than asking, do you know all the details about this experiment, which you might not have done. Okay, that's something which you can assume. If they're describing how someone does an experiment, they're probably going to ask you what are the possible problems with this experiment. So 1A, what is likely to have been the main source of error in this investigation? You're watching that ball bearing drop and you've marked the marks on there. There are a few different sources. The student measured the time taken for the ball bearing to fall different distances. You might have made errors marking the marks on the tube. I mean, it says that they're supposed to be 10 centimeters apart, but they aren't necessarily. You could have made errors when it comes to dropping the ball bearing. Maybe you held it a bit higher above the oil and so it was falling faster when it hit the oil. But probably the most likely source here is going to be that the student just didn't manage to hit the timer at the correct time. Now what I'm going to do, is this in the right place? Let me just move this over a little bit. There we go. What I'm going to do, oh good, and there's the far side of it, is record what my answers are on here so that when I go through, I can then mark them and we can see whether or not I would have got the marks, rather than me trying to remember. So for 1A, I'd put simply the student incorrectly timing the ball falling between marks. Okay, it's a relatively long answer for 1 mark, but I want to be exactly clear that I'm thinking it's going to be the student who's making the error here. Okay, let's look at the next question. So 1B, it shows the student's results plotted as a graph. The student has identified one of the results as being anomalous. Use the correct answer from the box to complete the sentence. The anomalous result was caused by the stopwatch being started, something the ball bearing was released. Well, we can rule out as straight away, because if it was started as the ball bearing was released, that's what's supposed to happen. So it's either after or before. And what you've got to look at there is that for that distance, this is an interesting one. They've plotted the graph a strange way round here. Personally, I would have done distance on one side, distance on the horizontal axis and time on the vertical axis, because really time is your dependent variable here. So they've kind of got it the wrong way round there. That's a tricky way to present it. But let's have a look. So I'm having to think a little bit here as well. So at 50 centimeters, they've got a time that's a bit too big, basically. So the only way that they're going to get a time that's a bit too big is if the stopwatch is running for longer, which means it has to have been started before. So 1B, part 1 is before. 1B part 2, what can you conclude from the graph about the speed of the ball bearing during the first 4 seconds? Again, this is only 1 mark, and what we can see is that because the graph is curving, the speed has got to be changing. In fact, we can figure it out because we've got a distance and a time as well. Speed is just distance divided by time. So you'll see that where we're getting a steeper graph there, let's see, just a sec. So it doesn't fall very far in the first second, and it falls an increasing distance over the next few seconds. So really, B part 2, it's accelerating. Do you know, I was worried that I was going to spell that wrong there as well. You may see some incorrect spellings. That's why I'm a science teacher, not an English teacher. But that is the correct spelling of accelerating. B part 3, the graph shows that the ball bearing reached its terminal velocity. Describe how the graph would be used to calculate the terminal velocity of the ball bearing. That's very simple. It's a distance time graph. So calculate the gradient. Now I'm taking a little bit of a chance here, because they could want you to describe how to actually calculate a gradient. But on these sorts of questions that I've seen before, they tend to be okay with you just saying, I want to calculate the gradients. Right, 1B part 4. The directions of the 2 forces acting on the ball bearing as it falls through the oil are shown in figure 3. Explain in terms of the forces shown in figure 3 why the ball bearing reaches its terminal velocity. Anytime it's talking about a falling object, so this could be a skydiver falling from a plane, or any falling object falling through a fluid like a gas or a liquid, it's eventually going to reach its terminal velocity, because there are 2 things which happen. The weight causes it to accelerate and fall faster and faster and faster, and as an object moves faster, it experiences more of the friction or more of the drag or more of the air resistance, which is tending to have the opposite effect and stop it accelerating. So I think all they're wanting here is, and this is part 4, I hope I'm going to have room for all of this on my piece of board here. Let's see. The weight causes it to accelerate. Which causes the drag to increase. Now I suspect that's all just the first mark on the mark scheme, because all I've really said is that it's falling faster, it's accelerating, the drag's going to increase, and it is only 2 marks. They want you to get that idea that then the weight equals the drag. So that eventually weight equals drag. Okay, it's possible that they wanted me to talk about resultant force here. Again, I'm going to take a chance, and I'm not going to mention resultant force because it is only a 2-mark question. We've got the idea that weight is going to equal drag, and so it's not going to accelerate. Well, have I said it's not going to accelerate? I'm gonna actually add an extra note. Resultant force equals 0 newtons. So the acceleration equals 0 meters per second. It's possibly overkill there, but I would like to get all of this right. And we're nearly at the end here. So 1 part C, the student repeated the investigation using warmer oil. Figure 4 shows a set of results using the warmer oil and a set of results using the cooler oil. So I'm looking at those 2 pictures there, and I'm seeing that it's actually speeded up in the warmer oil. It's covering the distance in less time. It's getting to 60 centimeters in less time. So it's falling faster in warmer oil. Straight away I can tell that. Use a correct phrase from the box to complete the sentence. After falling 40 centimeters, the drag force on the ball bearing in the warmer oil is less than. So 1C. The answer is less than. The drag force on the ball bearing in the cooler oil. Explain the reason for your answer. Okay, so that's the first part of my answer. So I'm just going to put what I identified in the previous bit. The ball falls 60 centimeters in less time. So it's got higher terminal velocity. Okay, that's taken me a little bit more than the 9 minutes which you should really spend on a 9-mark question like this, but I have been stopping to explain my thought processes as well. So I hope that's been clear. Let's just look at my screen here. Hopefully you can read my writing as well. Let's have a look at the mark scheme now, because that's all of question 1. So, mark scheme for question 1. Let me just pick up that pen lid I dropped as well. Let's see if I've got a red pen. I know I've got one in here. There we are. Right. So, on the mark scheme, for 1A, the acceptable answers were starting or stopping the stopwatch or timing over the smaller distances. Yes, so I get the mark there. So that's 1 mark. And what I'm going to do is I'll keep a track of what my overall mark for each question is up here as well, so we can see whether I reach the 46 and get to an A star grade. 1B is before, so there goes the other pen lid. These don't stay in there very well. I'm just going to not put them in there in future. So before is the correct answer, so another mark there. And then let's see, 1B. Oh, the acceptable answer. I can't remember what the question was. The acceptable answer was, well, they wanted increasing, but they would accept accelerating. So I do still get the mark. I'll be interested to see what that question was. Let's see. 1B part 3, calculate the gradient. Oh, wait a minute. Now for this, they say calculate the gradient of the straight / steepest / constant section, but they would accept gradient of any section after 5.5 seconds or 30 centimeters. So I don't get the mark for that. That's good, isn't it? I've already lost a mark. Purely because I haven't been specific enough about what gradient I'm going to calculate there. Oh well, let's hope that I don't lose too many more marks. The next bit, the drag force increases as the ball bearing gets faster. Okay, so there's a mark for that. Until the drag force equals weight, and they've actually written drag equals weight. So almost exactly the same as I've got there. And they do actually go into, they would have accepted that as well. So either of those points, this one or that one, would have been fine. But I get the 2 marks on that one. And 1C less than. And the ball bearing increases speed at a greater rate, or the ball bearing has a greater acceleration. No, I haven't mentioned that. Or terminal velocity has not been reached, so resultant force must be greater. Or as weight is the same, the drag must be less. Or it travels the same distance in less time. So I've got a mark for that bit. But I'll need to double check actually on the graph, but it says that they didn't reach terminal velocity. So that's a funny one. But fortunately, I had said it covered the distance in less time, so I do get the 2 marks for that. So in total, 1, 2, 3, 5, 7. Okay, so for question 1, I'll just record it up here. That was 7. Where else did I? Oh, there were 2 marks on that. So the resultant force must be greater. As weight is the same, the drag must be less. They wanted more detail on this answer. I really needed to talk about the resultant force being greater, or as the weight is the same, the drag's got to be less. I'm not sure that's entirely what the question asked for, but that's a little bit annoying. So, question 1, I've got 7 out of 9. I've already dropped 2 marks. What a fantastic start. So let's go back. Let's just have a quick look at what sorts of comments people are making. Okay. Right. Jamshid Al-Said. How can this guy even focus when there are all these anonymous teenage trolls on there? I'm a teacher. I deal with teenagers all the time when they aren't anonymous. So that's how I manage. But there we go. Not the best score for that first question. I'm going to have to try a little bit harder. I'm also going to try and get this a bit more level. There we go. Hopefully that's a bit clearer. But there we go. So that is the first question. I'm not sure if I'm going to have time to go through all of these in this live stream, looking at the rate that I've gone through that one, because that's taken about 20 minutes to complete and discuss and then mark. It might be that I run a second live stream for the second half of the paper. We'll have to see how this goes. But let me just rub this off and I'll get started on question 2. Okay, so question 2. I'll leave the lid there. Alpha particles, beta particles, and gamma rays are types of nuclear radiation. This is something which is almost always on the exam paper, where they want you to understand what the 3 different types of radiation are and what their properties are. They're not necessarily going to ask you about every last property of them, but they're probably going to want a bit of detail, and I'm expecting to see somewhere in here them asking what is an alpha particle or what is a beta particle. So let's see. Oh yeah, 2A. Describe the structure of an alpha particle. A helium nucleus. I'm just going to put, so that I don't lose any marks, 2 protons plus 2 neutrons. Okay, a very, very standard question there. 2B, nuclear radiation can change atoms into ions by the process of ionization. Which type of nuclear radiation is the least ionizing? That is just going to be gamma. Or gamma rays in this case. Again, you need to make sure you understand that. But the short version is alpha particles are the biggest, heaviest ones. They cause the most damage when they smack into things. Gamma rays technically have no mass at all, so they cause the least damage. Now, that's not to say you'd really want to expose yourself to gamma rays, but they do cause the least damage out of the 3. What happens to the structure of an atom when the atom is ionized? This is something which doesn't just come up in physics, it also comes up in chemistry. So, let's see. Oh, that was B part 1, wasn't it? B part 2. It's a very simple answer. Ionization is causing a particle to be charged, and the way radiation will cause a particle to be charged is by causing it to lose electrons. So, really simple answer there. I say that, I'm a bit worried now that I'm going to lose a mark somehow, but I'm going to leave it as that. People working with sources of nuclear radiation risk damaging their health. State one precaution these people should take to reduce the risk to their health. This is a fairly easy one compared to the sort of question which you normally get on this, where you normally have to evaluate what the risks are, make some sort of assessment of, is it safe for these people to live in this particular place? So for example, in Cornwall there is an awful lot more granite than there is in other parts of the country, and there's a slightly higher risk of radon exposure, and so the question might ask you, is it safe for people in Cornwall to remain living in Cornwall? And the answer is really yes. Although there's a slightly higher risk, making sure that things like basements are properly ventilated will mitigate most of that risk. It's not a huge risk. In this case though, they just want to know the precautions. So there are loads of different things, but make sure you're talking about people working with sources of nuclear radiation. So I'm going to go for a really common one. Store, oops, can't write. Sorry. Store the sources in lead lined boxes. That was actually a question on one of the EdXL papers I was just looking at recently with my own Year 11s. It's something that crops up loads and loads of times. There are lots of different possible ways that you could make it safe to handle these. You could wear protective clothing, etc., etc. But making sure that they're stored in lead-lined boxes is going to be fine, I think, for this one. Oh, and then we've got the 6-mark question. I did mean to have a good look through this paper and see where the 6-mark questions were, but I just jumped straight in. So let's have a look. In this question, you'll be assessed on using good English, blah, blah, blah. The type of radiation emitted from a radioactive source can be identified by comparing the properties of the radiation to the properties of alpha, beta, and gamma radiation. Describe the properties of alpha, beta, and gamma radiation in terms of their penetration through materials, range in air, deflection in a magnetic field. And there's 6 marks on this. So this, as far as 6-mark questions go, particularly for AQA, this is a nice, easy one. Whoever was doing this paper last year, I hope you felt that this was a nice, easy one. I've seen much worse ones, because this is some very, very standard information. They're just asking you to state the properties of these. And that's a 6-mark question. They're not asking you to make an informed comparison about anything. They're just asking you, what are the properties? So, you need to talk about penetration, range in air, and deflection in a magnetic field. So I'm just going to go through each of the different types of particle in turn. Alpha particles have a short range in air, around 1 meter or less. This can actually depend on the energy of the alpha particle, that is how fast it's moving, but it's typically pretty short. I might be overestimating it with 1 meter. It can be just centimeters. In fact, you know what? I'm going to change that. I'm going to reword it seeing as this is a 6-mark question. Oops, several centimeters. They don't penetrate material as well. And can be stopped by paper. And the deflection in a magnetic field they're charged, so can be deflected by a magnetic field. Now that's quite a lot of information just to talk about alpha particles when I still need to do beta and gamma, but with beta and gamma I can then refer back to my statements here. Now notice that the key bits which I'm talking about here I've just mentioned in individual sentences. There's one sentence for each of the things which they've asked me to mention. So they will be looking for some sort of structure to your answer. That would be the sort of thing which would be fine to get you the marks. Let's see, so next. Beta particles. Travel further through air. One or 2 meters or more, but the idea that they're not traveling huge distances. And can be stopped by several millimeters of aluminium. That's the standard one which they always talk about for beta particles being stopped. Aluminium is referred to quite a lot for a simple reason really. It's not very dense and it's relatively cheap as well. So you can make a fairly lightweight way to stop beta particles, even potentially a wearable way to stop beta particles, but certainly something which could be applied to say a room or a vehicle without it being a big problem. Gamma rays, of course, they're much more difficult to stop, but aluminium, with it being light and with you not actually needing that much, aluminium's a pretty effective way to shield from beta particles. Let's see. Oh, and I need to talk about their charge. They have opposite charge to alpha, so are deflected in the opposite direction by a magnetic field. I suppose I could mention here that they would also be deflected by a greater amount because they've got less mass and so they've got less momentum. But I'm not going to put that in there. I'm going to take my chances because I've got quite a lot of information about beta particles there. Finally, gamma. They did want gamma, yes. Gamma rays travel very far through air and need several centimeters of lead. Oh, can't spell lead, that's worrying. To be stopped. They aren't deflected by magnetic fields. As they're uncharged. I'm running out of room here. Okay, and that's the end of that question. That is a really complete answer for the 6-mark question. But I figure some of you will be wanting to refer to this as part of your revision as well. So that should hopefully cover everything. Am I at the end? Yes, I am. So let's have a look and see how I did. Hopefully, I've scored a bit better. Oh, leave the lid there again. So for question 2. This was out of 10, by the way, was question 2. So for 2A, they would accept 2 protons and 2 neutrons, or they would have accepted it's the same as a helium nucleus. So that was just fine. I get the mark there. I would have got the mark for either of those bits. The next bit is gamma rays, so I got the mark there. The next bit, they would have accepted losers or gains, 1 or more electrons, so that is fine. Yes, I've forgotten, of course, if it's a beta particle hitting something, it could gain electrons because they are electrons. But losers electrons would be fine. Again, that crops up in chemistry, so that's a fairly easy one for you, relatively speaking. Now for 2C, they would have accepted all sorts of different things. Wear protective clothing, work behind lead or concrete or glass shielding, limit the time of exposure, use remote handling, wear masks or gloves, wear a film badge, handle with tongs, with really long tongs, maintain a safe distance, avoid direct contact, all sorts of different things. I've talked about making sure that they're out of the way in lead, so I think that is worth the mark there. They wouldn't have accepted wearing goggles. That wouldn't have given enough detail, and a pair of goggles probably wouldn't make that much of a difference. Likewise, they wouldn't have accepted wear protective equipment or gear. You needed to say specifically what it was that they needed to wear to make sure that they weren't getting those sorts of radiation into their bodies. And next, let's see how I did on this. So this is more promising so far. Let's see. So, to get 1 to 2 marks, there should be a description of at least one type of radiation in terms of 1 or more of its properties. Well, I've got all 3 types there, so hopefully I'm past that. For 3 to 4 marks, there's a description of at least 2 types of radiation in terms of some properties, or a full description of 1 type of radiation in terms of all 3 properties, or the same properties described for all 3 radiations. So if I'd gone down here and I'd said alpha particles are stopped by paper, beta particles are stopped by several millimeters of aluminium, gamma rays need several centimeters of lead to be stopped, that's probably going to be getting me 3 marks on this. That's not bad for a 6-mark question, because you're leaving most of the information that I've got out, and yet you're still getting half the marks. Remember, with 6-mark questions, the most important thing is that you try. Loads and loads of people just get put off by the 6-mark questions. Getting all 6 marks is tricky, but getting some marks is really, really easy, and you can't afford to just chuck those away, so do have a go at them. Let's see, so they wanted, for alpha particles, that they're the least penetrating, that they're stopped by paper or cards. So what I'm going to do is just go through here, tick relevant points. So stopped by paper, they don't penetrate materials well, yes. They've got the shortest range, travel centimeters in air, yes. They're slightly deflected by a magnetic field, yep. So I've talked about the key things that I need there. Beta particles, they'll be stopped by several millimeters of aluminium. They can travel 1 or 2 meters in air. Deflected by a magnetic field in the opposite direction. So they are deflected and it's the opposite direction. And gamma rays, travel several centimeters through air. Yes, they are most penetrating and they aren't deflected. Oh, I misspelled deflected there. I missed the D off the end of it. I don't think for that one spelling mistake that would rule me out getting the quality of written communication mark. Generally speaking, you're allowed maybe 1 or 2 errors for that. I think everywhere else in here I've spelt things correctly. Let's see. Travel very far through air, stopped by that, and then not deflected by a magnetic field. So, I think there that I've got complete information about all three, and I've also, aside from that one mistake there, I think all my spelling and punctuation and everything is correct. So I hope it doesn't seem too egotistical for me to give myself a 6 for that. So question 2, done a little bit better. That was out of 10, and I reckon I've scored a 10 on that. Maybe you disagree, I don't know. I don't really have time to read everyone's comments at the moment. I'm trying to get some of them there, but hopefully you'll be able to see the sorts of things which you needed in that answer. I just got really put off by what someone said on there. I'm not going to repeat it, but goodness me, folks. Very strange. Right, let's get on to question 3 then. How long have I been going? Oh, about 40 minutes. Yeah, I don't think I'm going to get all of this done in the hour. Not with all this talk as well. But we'll see how we go. Okay. There's a question paper. There we are. Question 3. Figure 5 shows the inside of a battery pack designed to hold 3 identical 1.5 volt cells. As soon as I look at this, I'm immediately thinking they're probably going to start talking about things being in series and parallel. But we'll see. So 3A. Which one of the arrangements shown in figure 6 would give a 4.5 volt output across the battery pack terminals T? Oh yeah, so this is just cells in series. You need to make sure all the cells are the same way round. Now that doesn't mean that they should be lined up the same way on the page. That means that it should go from the positive terminal to the negative terminal, and then the next cell should be positive to negative, and then the next cell should be positive to negative. They should be the same way round as you go round the circuit. Basically the same way round from the point of view of the electricity. And the only one where, as you go round the circuit, they're all facing in the right direction is the third one. That's the correct one. I'm not going to draw the whole circuit out because you can look at it on the exam paper yourself. Let's keep going. So 3B shows a variable resistor and a fixed value resistor connected in series in a circuit. Now the first thing that I want you to do, anytime you see a circuit where they've drawn it like that and they've drawn the voltmeters and the ammeters in there, just try and ignore them. Try and overlook those voltmeters and ammeters, because if they're connected correctly, they shouldn't affect how the circuit works at all. You can even redraw the circuit, and I'm going to do that. I'll redraw it over here, leave myself some room to answer. But this is really all that the circuit is. One variable resistor, one fixed resistor, like that. That's R. You can ignore those meters. Same with ammeters, so long as they're connected correctly, you can ignore what they're doing. So if it helps, redraw your circuits. Complete figure 7 to show how an ammeter would be connected to measure the current through the circuit. I should have read the question before I started talking about that. So I am going to have to redraw the whole thing. Okay, let's see. I'll put it over here so it's with all my other answers. There's R. Fine, there's V1. That V2, yep. Now, there's all sorts of different places where you could put an ammeter in this. It just needs to be in series with these two. So anywhere around here or around here would be in series, or right in between them would be fine as well. I'm just going to put my ammeter there. And that'll do. Okay, but anywhere around here would be fine, in between the two, and anywhere around there would also be fine. Any of those places would be acceptable locations for the ammeter. Let me just rub that out. (3C). The variable resistor can be adjusted to have any value from 200 ohms to 600 ohms. So, a variable resistor, it's just like a dimmer switch which you might have in your home. and you can turn the value of that resistance up and down. Obviously, if the resistance is greater, then it's going to mean that less current can flow through here, and vice versa. So figure 8 shows how the reading on the voltmeter V1 and V2 change as the resistance of the variable resistor changes. So there's voltmeter V1. As you turn up the resistance, this gets a bigger voltage across it. And this one, at the same time, gets a smaller voltage across it. So you've got a fixed amount of voltage here. As this one gets bigger, it gets a bigger share of that. And as that one is smaller relative to that one, it gets its smaller share. But basically this one, the bigger this one is relative to the other, the greater a share of that voltage it gets, or potential difference we really should say. Remember, by the way, potential difference, voltage, they mean the same thing. They will always use the term potential difference on the exams, but usually they accept the word voltage, meaning potential difference, in the mark scheme. So don't worry if you write voltage in your answer. How could the potential difference of the battery be calculated from figure 8? Well, it's 12. Yeah, 9 plus 3 volts equals 12 volts is the correct answer there. So 9 plus 3 volts. Oh. They haven't written the V after those, have they? Equals 12 volts is the correct answer, but they want a reason for that answer. If you look at any point on this graph, the total voltage, the total potential difference of V1 and V2 always adds up to 12. This is just what we call a potential divider. So I'm going to say the total potential difference is shared across the resistors. Not sure if that's going to be a clear enough explanation for them or not. This is where it gets a little bit complicated. My degree is actually electronic and computer engineering. I understand that. I'm unsure whether or not that explanation is going to be clear enough for the mark scheme. I'm going to add a bit to it just in case. So the total potential difference is shared across the resistors. Adding each. We'll give you this total. I hope that's going to be clear enough to get the mark. As I say, that's a funny one. If anything, it's that I understand it too well in this case. This is particularly my area of specialism here, so I might be losing the marks just because I'm not going into enough detail there. Right, oh, that was C part 1, wasn't it? One and C part 2. Use figure 8 to determine the resistance of the fixed resistor R. Give the reason for your answer. Let's have a look. It's pretty easy. It's 600 ohms. I thought I was going to have to do a Ohm's law calculation there, V equals IR, and work something out. They might still ask me to do that, but this is dead simple. It's 600 ohms as when the variable resistor is 600 ohms. Both resistors have equal shares of the potential difference, or PD for short. So if you look on the graph, I don't know, you'll be able to see this if I hold it up like that. Over there on the right of the graph, you see that the two lines meet. Where they meet is where the resistance is 600 ohms. It's not showing up very well, is it? Hopefully you're looking at this on your own copy as well. But where they meet, you've got the same potential difference across both of these resistors. So they must both have the same value in this case. And we know what the resistance of the variable one is because it says on the graph it's 600 ohms. So the other one's got to be 600 ohms as well. Let's see. 3C part 3. And this is the last bit of this question. Calculate the current through the circuit when the resistance of the variable resistor equals 200 ohms. Oh, so this is an Ohm's law calculation. So V equals IR, and I need to rearrange this for a start. Do have a video all about how to rearrange equations if you're not sure. If you're doing foundation tier, you won't need to do rearrangements of equations, but everyone on higher tier, you will. You do get given this equation on your formula sheet though. The only reason I didn't need to look it up is because I know them all off by heart by now because I've been teaching it for so long. Poor old year 10, you're going to have to learn this along with all the other equations. Anyway, so rearranging this, I'm going to move the R down here so I get that V over R equals I. So that's how I work out my currents. They've given us the resistance that they want us to use, which is 200 ohms. So I just need to find out what my potential difference, my voltage is. And so I look at where 200 ohms is. It's the variable resistor. So which voltmeter is a variable resistor? V1. So I want to know what the voltage is for voltmeter V1. So it's 3 volts. Okay, when the resistance was 200 ohms, from the graph, the voltage was 3 volts. And so I can put these into the equation now. So I equals 3 volts divided by 200 ohms. Can't do that in my head. I should have brought a calculator. Never mind, I've got one on my tablet. Just bear with me for a second. It's not open. Hold on. You see, I've made the classic mistake here, the mistake which so many people do make, which is I've forgotten to bring my calculator to the exam. Make sure that you learn from that. Anyway, let's see, I've got it up now. 3 divided by 200 gives me 0.015 amps. Amperes, I should say, if I'm being strictly correct. Oh yeah, and they give you the units there. So there's just two, oh, there are 3 marks on here. So I guess the 3 marks, there was one for being able to read this number off the graph. I guess there was another one for rearranging your equation correctly and putting your numbers in, and a third one for figuring out the correct answer there. Right, let's have a look at the mark scheme and see how I did on this one. Still a bit nervous about that answer there, but we'll see. So 3A, third box from the left ticked, that's a mark. Correct symbol drawn in series, must have uppercase A, so yes, that's a mark. So a mark for that, and you'd only get the mark for the reason if you'd got that. The potential difference of the battery is shared across the variable resistor and the fixed resistors. Fixed resistor, I should say. So yeah, they would give you the mark for that. Good. If anything, I didn't need this extra sentence. That's good to see. You could have just written V1 plus V2 equals PD of the battery for that. Or you could have said PD is shared in a series circuit. If I recall correctly, in the AQA specification, there's just one sentence in there which says that you need to have an awareness that potential difference is shared in series. And it's literally out of pages and pages of information, there's just that one sentence. But clearly it was worth quite a few marks here. Okay, your total potential difference, the 12 volts which is coming from this, is shared out between those. And the bigger a resistor is, the bigger a share it gets. Now you don't need to know that second bit, that bigger resistors get a bigger share. You just need to know that it is shared out. But you may as well, because it was at least relevant to this question. Okay, so I've got both the marks there. I was worried about that one. The next one is 600 ohms, and then you needed your reason. The potential difference of the supply is shared equally when the resistors have the same value. So, yes, or the ratio of the potential difference is the same as the ratio of the resistance. So, I've got the marks there as well. Now, let's just put the totals here. And I am quietly confident about this. So, yeah, here we go. If you'd written 0.015 and hadn't done anything else at all, you'd get the mark here. However, there is a huge risk that somewhere along the way, you've made a little mistake or you've typed something into your calculator incorrectly. Always show you're working, because you've got, let's see, if you took they did that in a different way to me. I mean, it still worked, but they did that in a different way. Right, if you knew how to do the rearrangement here, that was a mark, basically. If you got the numbers correctly off the graph and you were substituting them incorrectly, then either that bit or that bit, you'd get another mark, and then there was the final mark for that bit. I mean, it's 3 altogether, but if you were just reading the right information off the graph and stating what you were going to do with it, if you'd rearranged this incorrectly but you'd got this bit, you'd get a mark. Okay, so always show you're working. So on this one, this was out of 9. Did I get all 9? 3, 5, 7, 8, 9. Yes. So what am I on at the moment? 10, 19. I'm on 26. I've only dropped 2 marks so far. On the first question, on the easiest question, I dropped 2 marks. That is fairly typical. I'm going to do one more question on this, because I think we're starting to overrun, unless I really fly through the next one, because I don't want to spend forever on this. And I think I'll come back to the next questions later on. Let me just check how many questions there are. So we're on question 4. Oh, that is quite a long one. There's also question 5, which is really long. And there's question 6. So I'm going to leave questions 5 and 6 for another live stream at another point. I'll decide when that's going to be at some point in the near future, and I'll continue it. Possibly in the next couple of days, I'll finish this paper off. But let's get on to question 4. Okay, what are you lot saying in the comments, by the way? Okay, some more weird comments in there. And some people saying that they're going to fail. Be more confident. Have a go at stuff. So long as you do the practice revision, you're going to be fine, okay? Just do your best. That's the important thing. Baba Lala, I'm not your dad. Laura Rose, I'm not your dad either. Very, very weird there. Let's see. So, 4A. A washing machine is connected to mains electricity using a mains electricity supply using a cable and a 3-pin plug. And figure 9 shows a 3-pin plug, just in case you didn't know what one of those was. Name the materials used in the structure of the plug. Give the reason why each material is used. I mean, the outer case is plastic. That's straightforward enough. The pin can be made of different materials. Typically, it's going to be steel. Here's the pin. Or sometimes it might be brass. It could be brass or it could be steel. Normally stainless steel. That is because it's a good conductor of electricity. And it's going to be strong, it's going to be hard, it's going to retain its shape. So you want to make the pins out of something which can be shoved into a plug socket and taken out of a plug socket repeatedly without it breaking, and you also want it to conduct electricity. They're probably just looking for metal here, or maybe that's not specific enough. Something like lead wouldn't be any good. They might also be looking for a comment that it needs to be something which stays relatively shiny. I'm going to leave that for now. Maybe they were looking for stainless steel, but I'm going to leave that. I'm going to take my chances. The outer case. This is going to be a heat resistant plastic. This is because it's a poor conductor. So you don't get any electric shocks. And it's non-flammable and rigid. You want a plastic which, if there's some sort of fault in there, it isn't going to start melting, and it also isn't going to set fire. 4B. The 3-pin plug contains a fuse. The fuse is connected to one of the wires inside the cable. Which one of the wires inside the cable is the fuse connected to? Dead simple answer. That is the live wire. Oh, that was just 4B part 1, wasn't it? Let me rub that out. Keep doing that. 4B part 2. The fuse is a thin wire inside a closed glass tube. The wire acts as a resistor. What effect does a current through a wire have on the wire? It makes its temperature increase. I feel like this is a question where when we look at the mark scheme, they'll specifically say it gets hot isn't a good enough answer, because it isn't necessarily going to get what we consider hot. It might just get marginally warmer, maybe half a degree warmer. Generally speaking, that's what we'd want. Sometimes it's going to get really hot, and sometimes it's going to melt. That's the purpose of a fuse. But I suspect they won't accept that answer. We'll see though. 4B part 3. The power of the washing machine varies between 0.7 kilowatts and 2 kilowatts, depending on which part of the wash cycle is operating. Calculate the maximum current drawn from the mains electricity supply by the washing machine. The supply is at a potential difference of 230 volts. Use the equation from the physics equation sheet. So we've got, let's see, calculate the maximum current. So that's going to be when we're getting the maximum power. So let's say our power is 2 kilowatts. Now, they've given you a power in kilowatts, so you're going to need to convert that into watts. Kilo just means 1,000. If someone said that they were going to pay you 2K, I'm sure most of you would know that that meant 2,000. In this case, same thing. 2 kilowatts is just 2,000 watts. And the mains electricity supply is at a potential difference of 230 volts, so V equals 230 volts. And the equation which I'm going to use to link the power and the potential difference and the currents all together is just this one. P equals I times V. So I'm going to move my V down there, and I get that P over V equals the current. And so that's going to be 2,000 divided by 230. And again, let me switch to my calculator because I can't do that in my head. 2,000 divided by 230 equals, now I've got an answer here with a lot of digits. Let me just hold that up there. Loads and loads of digits there. If you get an answer like that on your physics exam, don't write all those digits down. There is no way that we can measure things to that degree of precision. I mean, that's, let's see, that's milliamps, microamps, nanoamps. you're getting down to picoamps with that measurement. We're not going to take measurements that are that precise. So I would round that to 1 or 2 decimal places. Rounding to 2 decimal places will give me 8.70 amps. Because it's 8.695 and you round up from that 5. Okay, but there's my answer. 4C. Nearly done on this question. Figure 10 shows how the mains electricity cable is connected to the washing machine. The earth wire is connected to the metal case of the washing machine. Earth wires are always connected to the metal cases of, well, basically anything that's using mains electricity and has a metal case. If a fault makes a metal case live, this is why they're always connected to those cases, the earth wire and fuse inside the plug prevent the mains cable from overheating and causing a fire. Explain how. So all this is the idea that the electricity from the live wire will be conducted through the metal case to the earth wire. Okay, I suspect that is just 1 mark for that bit. And this is a 2-mark question, but that's what your earth wire is there for. If a live wire touches the case, the electricity is then conducted to the earth wire. That hasn't made the appliance safe yet, but that metal case is going to have really low resistance, so you're going to get a large current flowing, and that melts the fuse. The large current which flows melts the fuse. Oh, actually, let's see. Prevent the mains cable from overheating. So they do want a little bit of a note about what's going on, just to be safe here. Stopping the electricity by breaking the circuit. I have probably given way more detail than I need there. I mean, looking at the number of lines there, and it's only 2 marks, that's probably more detail than is strictly necessary, but hopefully it's going to be enough information to get the 2 marks. And finally, D. New research has shown that many people underestimate the hazards of using mains electricity. It's important that people do understand the hazards of using mains electricity. Suggest why. 1 mark. That's a bit of a funny question, really. I mean, so that they don't get electrocuted is ultimately what you're getting at there, I guess. But how to phrase that? I'm going to put, if people understand the dangers they're more likely to take steps to avoid electrocution. I think that's probably going to be enough detail there. Right, let's have a look at how I've done for this one. Just a sec. So, mark scheme. For A, the pin is made from brass because it's hard and a good conductor. Yeah, they're not always made from brass, actually. They are sometimes made from stainless steel. But, yes, it was just 1 mark for saying what it was made from and that it was a good conductor and it was hard. Which is quite a lot to say just for 1 mark. And the outer case is made from plastic or rubber because it's a good electrical insulator. You could have said it was a good heat insulator as well. But yes, I've gone into way more detail than I needed there, but I've got the marks. So live, correct, I get the mark for that. Oh, it makes it hot or makes it warm. They would have given you the mark for that. Saying it melts, they wouldn't have given you the mark for that. But yes, makes its temperature increase. Definitely give you that. This one, you would get 1 mark for this substitution. So knowing that you're doing 2000 divided by 230. And you get your second mark for your 8. Well, actually, they've stated 8.7 on here. If you'd rounded it, you would have got that as well. But either way, I've got the marks there. And if you hadn't converted from kilowatts to watts, but you'd got an answer out here, which would have been 0.00087, then you would have got 1 mark on this. You wouldn't have got both because you forgot to do that conversion. 4C. A large current goes from the live wire to the earth wire. Large current flows from the live wire to the earth wire, so yes. They wouldn't accept electricity, a large amount of electricity. They wouldn't give you that. They want you to talk about the current flowing. I hadn't even thought about that in this answer, but there you go, I did get it. So remember, it's the current which moves around. That's what the electricity is. It's that flow of current. The potential difference is just the push which makes it move. And that causes the fuse to overheat and melt. So it melts the fuse. You could have said it blows the fuse. It wouldn't be enough to say it breaks the fuse or snaps the fuse. And you couldn't say it blows up the fuse either. There's not an explosion. Yeah, so I've got my 2 marks here, although I went into way more detail than I strictly needed. But better safe than sorry. And finally, I'll reduce the chance of electric shock. That's all they wanted there. They would have accepted reduce the risk of an accident. They would have accepted prevent electric shock, prevent electrocution, prevent or reduce the risk of an electrical fire. You could have written an electric shock can kill you, or you could have said it can kill you, or so you can use it safely. They were giving marks away for anything on there, really, weren't they? But I think I've got all the marks there. Let's see, so 2, 4, 6, 7, 8, 9. So question 4, I've got 9. So 9, 18, 28, 35 I'm on so far. This is not going too badly. I'm putting in, aside from that very first question, a performance which is putting me on track for an A star. I've got 2 more questions, and let me just have a very quick look at how many marks there are for those questions. There's the question paper. Let's see. Yeah, so question 5 is 10 marks, and question 6 is 7 marks. Oh, and there's a question 7 here as well. I hadn't even seen that, which is 6 marks. So I'm going to come back to those another time. Possibly tomorrow. I'll have to see. I will tweet details about that. So if you check my Twitter accounts, which is just here, I'm going to tweet which paper I'll be doing after I finish this one. And hopefully that'll be a little bit later in the week sometime. And I'll tweet when I'm going to do that as well. I'll also tweet when I'm going to do the second half of this paper, because we are now... Ooh, how long have I been going for? I've been going for an hour and a quarter now. So I'm going to call it a day there for now. But thank you very much for tuning in and watching. Let's just have a quick look at who's in the live chat. Yasmin Ellis, you're welcome. Oh, he's going too quickly. Fen Pinto, no, I'm not your mum either. Let's see. Yasmin Ellis, yes, I read your comments. Rebecca K, thanks, you're welcome. This is going way too quickly. You need to slow down, guys. There's too many there. It's going too quick now. I can't even read them. Daniel Law, you're welcome. Sarah XO, you're welcome. Wow, that's getting crazy now. Okay, So I hope this was some use to you. If you've got any feedback, I'm going to be, well, YouTube should automatically process this and the video should be available for you to leave comments on, and I'll be able to see all those. But they're going up my screen way too quickly now for me to be able to read them, I'm afraid. So do please leave them there or get in touch on Twitter if you've got any suggestions about how I could improve this. This was a first time round. I figured there'd be some mistakes and teething problems, and there were a few at the start. But all that aside, I do hope this has been a valuable experience for you. Thank you, the 168 people who are still watching, for continuing to watch to the end. I do appreciate your support. And very best of luck in your GCSEs, in any exams which you've got coming up. I know some of those are coming up very soon now. And I'll see you next time. Let's just go to the outro.